Hello everyone, I once again welcome you all to MSB lecture series on interpretative spectroscopy. In the last class I started discussion on NMR, and also in the beginning what I would do is I would give little bit information about all these spectroscopic methods and then start detailed discussion one at a time. In my previous lecture I started with analytical methods and also some fundamentals about analytical methods, and I started discussion on NMR, and then I started IR. So let me continue from where I had stopped. The approximate time scale for structure determination using various techniques is very important. So that gives some information about the limitations or advantage of a particular technique when we want to use it as an analytical tool to understand the structure of a molecule. For example, if you see in case of electron diffraction, we can use up to 10 to the power of minus 20 seconds, or in case of X-ray it is about 10 to the power of minus 18, and in case of UV it is 10 to the power of minus 15. That means whatever the dynamic process that happens up to 10 to the power of minus 15 can be analyzed using UV visible spectroscopy, and in case of visible it is the time scale is about 10 to the power of minus 14. And in case of IR and Raman it is about 10 to the power of minus 13, and in case of ESR it can range from 10 to the power of minus 4 to 10 to the power of minus 8, and in case of NMR it is 10 raised to minus 1 to 10 raised to minus 9. That means basically whatever the dynamic process that is happening in the time scale of 10 raised to minus 1 to 10 raised to minus 9 can be analyzed using NMR spectroscopy without any problem. But if there is any dynamic process that is much faster than 10 to the minus 9, let us say 10 to the minus 10, probably NMR would not identify. In that case what happens, probably we have to suppress the thermic process by cooling the solution NMR sample to much lower temperature, so that the dynamic process falls within this range, so that we can study through NMR what is happening. And similarly, if it is much slower than 10 to the power of minus 1, then probably we have to heat the sample so that dynamic process would fall in this range. So this is what the information that gives. In case of fast kinetics, it is about 10 raised to minus 3 to 10 to the power of 2, and physical separation of isomers. If you see two isomers are formed in a reaction, and then whether we can do separately after crystallization, because if they have different morphology, then at least we need 100 seconds. That means for physical separation it should be greater than 10 to the power of minus 2 time scale. That means the isomers formed should not undergo isomerization within 100 seconds. As I mentioned, NMR is the most powerful tool available for organic and inorganic structure determination. It is used to study a wide variety of nuclei. I have mentioned somewhere here it is 1H, 13C is there, both 11 boron and 10 boron are there, and of course 11 boron is about 80% natural abundance is there, remaining is 10 boron. 10 boron nuclear spin is 3, whereas 11 boron is 3 by 2. Again 14N, I value is equals 1, and in case of 15N, I value is equals half, and 19F, 31P, 29 silicon, and 103 rhodium, 195 platinum, 183 tungsten. All of them have nuclear spin value of I equals half, but their natural abundance varies. We will see. I have a table that I would be providing you in this lecture. We have some selectivity. Not all elements in the periodic table have nuclei which can be analyzed through NMR. That means I have classified here different type of nuclei into 3 categories, and even and even. What does it mean? Nuclei containing even number of both protons and neutrons have I equals 0, and therefore they cannot undergo NMR. So that means whenever we come across nuclei having even number of both protons and neutrons, then they have 0 nuclear spin. In that case, what happens? We cannot use them in NMR measurement. Examples: for helium 12 carbon, 16 oxygen, 32 S. Next, odd. So that means nuclei with odd number of both protons and neutrons have spin quantum numbers that are positive integers. Examples include 14N, we have I equals 1, 2H deuterium, I equals 1, and 10 boron, I equals 3. All others, okay, the remaining nuclei, odd, even or even odd combination of protons and neutrons, all have spins that are half integral. For example, 1H if you take, I equals half is there, 17O, I equals 5 by 2, 19F, I equals half, 23 sodium, I equals 3 by 2, and 31 phosphorus, I equals half. So this is how you can classify. So simply by looking into the number of protons and neutrons in a given atom, we should be able to tell whether it's NMR active. If not, if it is NMR active, what is its I value? So this is NMR periodic table. This will depict the elements which have NMR active nuclei, and also it has all details one looks for to use effectively is NMR. And I have another table pretty good, because here the color code is given for different nuclear spin. You can see here red one is I equals half. We have plenty of elements are there here. Starting from hydrogen is there, francium, and all elements, the blocks in red are all having I equals half value. And then I equals 1, we can see very few are there. One is lithium is here, one is nitrogen is here. And when I equals 3 by 2, we have quite a few, all in yellow color here. You can see beryllium is there, sodium, potassium, rubidium, and all those things. Even among lanthanides and actinides we have. And then I equals 5 by 2 are in green color, and I equals 7 by 2 are in blue color, and also 9 by 2 are in purple color. So you can see here most of the elements have some isotopes which are NMR active. Let us look into the interaction of these NMR active nucleus with the magnetic field. So according to quantum mechanics, the energy associated with the interaction of each different orientation of the magnetic moment with an external applied magnetic field B is equal to the component of mu, so magnetic moment, along with field B naught times the magnitude of B naught. That means it can be represented using this equation here, E equals mu z into B naught. Each value of mu z is associated with a different energy level. For example, I have shown here, you can see orientation of nucleus with I equals 1 and angular momentum and magnetic moment vectors in a magnetic field. So let us see if this is the applied magnetic field, and if I equals 1, this is how we will be having the values of -1, 0 and +1, and if the I value is half, again this is the one, it is the same magnetic moment shown here and magnetic moment is shown here, and then these orientations will be with respect to the magnetic field. If this is magnetic field Z naught, so these are the orientations of 1 and 0 and -1 nuclear spins. Energy levels for the interaction of nuclei, I equals 1, half or 3 by 2 with a magnetic field B naught, and we are using another term called gamma. Gamma is nothing but the gyromagnetic ratio or magnetogyric ratio, and this is positive for I equals 1 and negative for I equals 3 by 2. So that means at a given value of B naught, the spacings of the energy levels are equal. At a given value of B naught, the spacings of the energy levels are equal. The difference in the energy levels increases as B increases. That one should remember. The gap between the spacings of energy levels increases with increase in the magnetic field strength. This is actually a boon, because many complicated spectra we get under low magnetic field can be enhanced for better refinement when we go for higher field. This is where the interest is there about making instruments having higher field strength. If the magnetogyric ratio is positive, then mu z equals gamma mi h over 2 pi. This implies that mu z and mi will have the same sign, and because of that one, E equals what we have is mu z B naught. The energy level with the most negative will have the highest energy. So this one. So this is what it shows here. as I said, these orientations also, you cannot have any orientations in between. For example, here in case of I equals 1, we have 0, plus 1, 0 and minus 1, and in case of half, we have plus half and minus half, whereas in case of 3 by 2, we have plus 3 by 2, half, minus 3 by 2. And similarly, if we have 5 by 2, then we will be having plus 5 by 2, plus 3 by 2, plus half and minus half, minus 3 by 2 and minus 5 by 2. So it goes 7 by 2 also, one can keep writing like this. Nuclei with negative magnetogyric ratio will have the highest energy for the most positive Mi value. So I have highlighted these parts are very important. So nuclei with negative magnetogyric ratio will have highest energy for the most positive Mi value. So let us look into the effect of magnetic field on nucleus in a more classical way. I will come back to that one. Since the value of mu z can never have the full value of mu z, mu and n, nuclear angular momentum vector, can never be collinear with B naught. If we imagine a spinning top as a nucleus, the rotational axis cannot be aligned with B naught. This is very, very important. That means when the nucleus is persisting or rotating under the influence of the magnetic field, the rotational axis can never be collinear with the direction of applied magnetic field. It's always tilted at an angle, must be oriented at some angle relative to B naught. Can be visualized with these spinning tops. You can clearly visualize what I said here. You can see here. A typical top can be compared to a precessing nuclei under the influence of the magnetic field. And with respect to the magnetic field, if you just try to see here, this is not really collinear, it is at an angle. Same thing is true in case of all these things. This can be compared to the rotating magnetic field generated under the influence of a magnetic field on nuclei. For example, something like this, if you see here, although under the influence of this magnetic field, they are rotating, rotational axis is not collinear with this one. It is at an angle. So that means a tilted spinning top, when subjected to a force, it precises about the direction of the force that you saw in the previous slide. Similarly, a spinning nucleus precises about the magnetic field B naught. In that case, the frequency of this precessional movement is given by omega. Omega is nothing but omega equals gamma B naught. So this omega is called precessional frequency or Larmor frequency. You can see here, this is how this, in the absence of the magnetic field, when the magnetic field is there, it will be at an angle and then it will start precessing in this one with respect to applied magnetic field, so B naught. So this, the frequency with which a nucleus precesses under the influence of the magnetic field is called omega, and omega is directly proportional to the gyromagnetic ratio of that nucleus and also the magnetic field in which it is precessing. So this precessional frequency omega is called Larmor frequency. Orientation of a spinning nucleus in a magnetic field is shown here. The orientation is not allowed by quantum mechanics to have this kind of things. It doesn't precise like this here. It will be at an angle here, you can see, and precision about B naught in this, it goes like this. This is what exactly happens for a non-zero nuclear spin kept under the influence of a magnetic field with magnitude B naught. Again, I am repeating here, a tilted spinning top when subjected to a force precises about the direction of the force. Similarly, a spinning nucleus precises about the applied magnetic field B naught. The frequency of this precessional movement is given by omega equals gamma B naught. If you want to change the angle of rotation with respect to B naught, we must apply a force which moves the rotation axis of the nucleus away from this. So that means if it is something like this, if it is precessing, to increase and eventually to take it from this one away from this one, what happens? We have to apply another field which is perpendicular to the applied magnetic field. If we apply another field perpendicular to the magnetic field, what happens? It will tilt the precessing nucleus away from the direction of applied magnetic field, and eventually when the flip changes, we say resonance has occurred. In NMR, this force is provided by a second magnetic field Bi oriented at right angle or perpendicular to the B naught. So that means here basically we have the B naught is there and you apply another one here, this is Bi. So this would take away the precession frequency of this nucleus when matches the frequency of this applied magnetic field, then transition occurs. When B1, that is the applied magnetic field perpendicular to the B naught, so that means when B naught rotates about, when B1 rotates about B naught with Larmor frequency, the two rotation fields are in phase. Two rotational phases are in phase. Now nucleus experiences another magnetic field about which it can precess. So now it will make an attempt to precess about the new applied magnetic field also. That can be seen here in this diagram. You can see here. Earlier it was B1 was not applied. Under the influence of B naught, it was precessing about B naught in this fashion, and the moment we applied a magnetic field perpendicular to the B naught, and if the frequency of this one matches the Larmor frequency of this one, what happens? The nuclear transition happens. Okay, it will move away, and then the flipping of the spin takes place, and it will be flipping and it will be going in this direction. So, changing the precessional angle with perpendicular rotating magnetic field. So, this is when it rotates with Larmor frequency, nuclear spin flips. The precessional frequency of nucleus about B1 is much lower than omega. Quantum mechanics limits the magnetic moment to only certain orientations. Rotation of B at Larmor frequency causes nuclear spin from one orientation to another one. So, that means basically that is what we do. After knowing the precessional frequency of a nucleus under the influence of B naught, we apply another magnetic field that is perpendicular to B naught with a frequency matching the Larmor frequency of that nucleus to have nuclear transition. That means we say nuclear spin flips. What is the selection rule for nuclear transition? This is very important. So, for selection rule for nuclear transition is delta Mi equals plus or minus 1. That means basically when the nuclear spin should change its value from plus 1 to minus 1 or minus 1 to plus 1. So, this is against we come across spin selection rule in case of electronic transition. In case of electronic transition, we say equals 0, whereas here it is plus or minus 1. We should remember that one. If we consider a nucleus with spin equals I equals half, let us say as simple as proton, have only two energy levels, plus half and minus half. It is placed in a magnetic field. We can calculate its Larmor frequency or energy necessary for the transition. So, whatever the Larmor frequency is there, that is the energy required for the transition from plus half to minus half level. If a proton is placed in a magnetic field of 2 Tesla, then delta E, which gives the transition energy, can be directly calculated using these formulas. For example, transition from energy level 1 to 2 is mu Z1 B naught minus mu Z2 B naught, that is equal to Mi gamma H B naught, that is equal to gamma H B naught. Now, if the change in energy is produced by electromagnetic radiation, then we know that delta E equals H nu, that is equal to H gamma H B naught. So, that was given here. If we consider Larmor frequency in place of nu, then it will become 2 because it is angular. Okay, it is rotating. So, as a result, what happens? Omega becomes 2 pi nu, then nu equals gamma B naught over 2 pi. So, that means we can now calculate the precessional frequency under different magnitude of B naught. We can calculate. So, here what is only known is, if we know the magnetic field strength and gyromagnetic ratio is constant, unique for each nucleus, and then we should be able to calculate this Larmor frequency very easily. Once we know that, we can tune the NMR instrument. So, this equation is very, very important, and this equation is nu equals gamma B naught over 2 pi is what you should remember. That is all, nothing else. You should remember this one. So, once you remember, most of the problems we come across can be understood and solved as far as NMR is concerned. So, now for example, let us say non-zero nuclear spin, we will be having all possible orientations in the absence of the magnetic field. The moment we apply magnetic field, what happens? So, they align. Some of them will be aligned with the magnetic field, some of them will be opposing the magnetic field. You can see here. So, for example, this is precessing with respect to B naught, and yes, when we apply another magnetic field Bi perpendicular to B naught, what happens? It flips. You can see here how this is flipping. This is what exactly happens in case of NMR. So here, as I mentioned, this equation is very important. For protons in a magnetic field of 2 Tesla, we know that gamma value is given. We should calculate now nu for this proton, 2 Tesla. So now it's very simple. You add your 226.78 into 10 raised to 7. So B naught is there. So into B naught and divided by 2 into 22 by 7. Okay, if you calculate, for example, 26.75 into 2 into 10 raised to 7 over 2 into 22, 7 comes here. If you simplify this one, it would come around, I would say, 90 megahertz. Okay, so this is how you can calculate the frequency starting from the gyromagnetic ratio and also the magnetic field strength. Okay. So similarly, one can calculate the radio frequency necessary for the transition of 11 boron, 31 phosphorus, 13 C at magnetic field strength of 2 Tesla and 10 Tesla. Okay. So this is how the orientations are there in the absence of magnetic field. The moment you apply magnetic field, they will align in such a way that some of them will be having plus half and some of them will be having minus half. So nuclear spin. What is nuclear spin? A nucleus with an odd atomic number or an odd mass number has a nuclear spin. That's what I was telling you. The spinning charged nucleus generates a magnetic field. Any charged species generates a magnetic field, and when you apply that one in the magnetic field, it will start rotating about the magnetic field. So that means here you can see here this is the spinning protons under the influence of the magnetic field generate a loop of current here, and loop of current, as a result what happens, you can see they behave like tiny magnets and aligning in this direction. They behave like a bar magnet. Typically I have shown here B naught is there. In the absence of magnetic field, they can be having all kind of rotations, orientations, and when you apply magnetic field, it will flip and probably it will go something like this, and this is low energy, more stable, and then if it has like this orientation, this is high energy, less stable. So this one we call it as plus half, and this we call it as minus half. Okay. So let me continue in the next class. Let me stop at this stage and continue more discussion on NMR in my next class.